Here we have a circle whose centre is at the origin of the axes here. Let's consider a radius that goes from the centre of the circle to the rim. Now we know the coordinates of this point here. It's 0, 0 because it's at the origin. Let's call this point over here point P, and given by the coordinates x, y. So that's a general point anywhere on the circumference of this circle. Now what's the relationship between the radius that we'll call r and the point here P, represented by x across and y going up? Well, if we drop a perpendicular here and bring a line across here, we'll get a right angled triangle. Then it'll make it easier for us to spot the relationship between the radius and the x coordinate and the y coordinate. Here we now have a right angled triangle. The distance from O, the horizontal distance from O to the point P, is given by x, and the vertical distance from O to point P is given by y. From this we can see that the relationship between r, x and y can be given using Pythagoras' theorem. That is, the equation of a circle whose radius is r and centre is at the origin can be given by x squared plus y squared equals r squared. Here we have another circle, but the centre is no longer at the origin. Let's say the centre is at the point Q, which has an x coordinate of A and a y coordinate of B. Let's draw on the radius to a point P somewhere on the circumference of the circle. Again, point P is a general point on the circumference of this circle given by x, y. Using the same approach as before, let's drop a perpendicular to fall in line with the horizontal line that comes across from Q towards P. Here we have our right angled triangle. Let's label the radius of the circle with an r, and then let's look at the horizontal distance from Q to P and the vertical distance from Q to P. Well, this distance here is the difference between x and A. So I can write this on here. From here to here is going to be x minus A. Similarly, this distance here is y minus B. Using Pythagoras' theorem, we can now get the relationship between the radius of the circle and this general point P on the circumference. This is the equation of a circle of radius r whose centre is at the point AB. You must learn this result. If we expand these brackets and simplify it, we get another form of an equation of a circle. Let's do that now. If we collect all of the constant terms together, we get the following. Here I've introduced a constant c to represent the sum of a squared plus b squared minus r squared. And that gives me an equation of a circle in this form. X squared minus 2ax plus y squared minus 2by plus c equals 0. Find the equation of the circle with centre at 3, -1 and radius 4. Well, we know the general form of the equation of a circle can be given by the following. This is where the centre of the circle is at A, B, and R is the radius of the circle. So let's substitute these values into our equation here. And now we can tidy this up. And here we have the equation of the circle. Expanding and simplifying this will give us the alternative form of the equation of the circle. Let's do that now. Here we have the equation of the same circle expressed in a different way. Find the centre and the radius of the circle that has this equation. Well, there are two ways to approach this. Here's method one, using completing the square. First, I like to rearrange this to collect the x terms and the y terms together. And now, I'll complete the square on the x terms and the y terms. I can now tidy this up. Now the equation of the circle is written in a much more familiar way. Let's compare it with the following general form. From here, I can see that the centre of the circle is at -1, 2, and the radius is the square root of 9, which is 3. Using the alternative method, I compare the original equation with the other general form. Here I can see that this 2, the coefficient of x, is equal to -2a, and similarly this -4, the coefficient of y, is equal to -2b. Comparing these gives me the following result. This means that the centre of the circle is at -1, 2, which agrees with what I have down here. To find the radius, I need to remember that this constant here, c, is equal to a squared plus b squared minus r squared. And now that I know the value of a and b, and I already know c is -4, I can calculate the value of r. This also agrees with the previous result that I had. If two circles touch like this externally, then the sum of the radii is equal to the distance between the two centres of the circles. So this radius here, we'll call that R1, plus this radius here, we'll call that R2, is equal to the length of this line. If we call the centre of that circle A and the centre of that circle B, we can then say if the circles touch externally, that is they meet at one point like this, then the length AB is equal to the sum of R1 and R2. Here, the two circles touch internally, that is they meet at one point where one circle is inside the other. Then what we have is the difference between the two radii equals the distance between the two centres of the circle. So we take the larger radius first, and we'll call that distance there R1, from the centre of the larger circle to its edge there. And then we've got the smaller radius, which goes from this point here right to the edge of the circle. So here to the edge of the circle, I'll draw it on separately so we can see. That's the second radius. Then R1 minus R2 gives us the distance between the two centres of the circle. So again, if we call the larger circle centre A and the smaller centre circle B, then the length of AB is the larger radius minus the smaller radius. Here I've got two circles that intersect. Remember, when they touch, they meet at one point. So when they intersect, they must cross at two distinct points. I want to find out the equation of this common chord that goes through the circles here. Here's the equation of the first circle. Here's the equation of the second circle. So the points where they intersect is where they share the same values of x and y at the particular point here and here. So let's solve these simultaneously. First of all, I'm going to take one away from the other. I'm going to use this equation, I'm going to rearrange it and substitute it back into one of the above equations. So here I have y equals 2x minus 3. I'm going to take this and substitute it back into the first equation. I can now expand the brackets, rearrange it and solve this equation to get my two values of x, and that'll be where this common chord intersects the two circles. Here I get two values of x. One is x equals 2 and the other one is x equals minus 1. Substituting these x values into this equation here gives me a y value of 1 when x is 2 and a y value of negative 5 when x is negative 1. So the 2 points that I've got here are negative 1, negative 5 and 2, 1. Now I've got the coordinates of intersection, I can work out the equation of this line. First of all, let's work out the gradient of the line, because remember you need two things, the gradient of the line and a point on the line to get an equation of the line. So I've got these 2 points, one is at 2, 1 and the other one is at negative 1, negative 5. So the gradient is the difference in y, so that's 1 minus minus 5 over the difference in x, which is 2 minus minus 1. So that gives me a gradient of 6 over 3, which is 2. And then I can use one of the points. I'm going to go for the one that has positive values to get my equation of the line. Y minus y1, so that's y minus 1, equals the gradient 2x minus x1. And tidying that up gives me y equals 2x minus 4, and then I'm going to add the 1 to both sides. So that's y equals 2x minus 3, and that's the equation of the common chord.